Hello from Team Chakravyuha. This is a demonstration video of our solution prototype for the problem statement ID SIH25236. The problem statement is concerned about creating an application software to obfuscate object files using low-level virtual machine, that is LLVM. The theme for the problem statement is about blockchain and cybersecurity, and the problem statement is presented by NTRO, that is National Technical Research Organization. The world today revolves around technology, and this tech relies on software that almost always has a threat of being reverse engineered. This is a critical consideration that needs to be addressed by making the software harder to reverse engineer. Many organizations lose billions in revenue due to piracy and illegal usage of their intellectual properties. The sectors such as defense, finance are highly vulnerable to such threats. This is the root directory for the our demonstration. In this root directory, we'll create a LLVM pass via a shared object file that would be built in the build directory. Uh, we'll first have to create the shared object using CMake. CMake is a build tool that we're using in order to create this shared object. This shared object would be later used via an optimizer to create the obfuscated code from the intermediate representation of the code that is supposed to be obfuscated. Let us verify if the shared object has been created or not. Uh, this can be done by a simple ls command. Now that the shared object is created, we can test if the pass works or not. We'll do that by simply compiling the source code in the test directory, which is test underscore a dot c via clang. We'll pass the flag emit LLVM, which would emit the intermediate representation file in the build directory. This intermediate representation is later passed to the optimizer. As you can see, these along with the passes that we want to implement. Here we want to implement all of the passes, so we are uh, mentioning all the passes that we want to implement, and this creates an obfuscated uh, intermediate representation, which along with a report that both of which are stored in the build directory as well. Now, in order to have a comparison, will also create compile the original code without obfuscation. Now let us think like a reverse engineer. The first time a reverse engineer gets a executable in its hand, he would try to run the command strings on it. The strings command would return every string that is present in the executable. Looking at the output, it seems like the string chakra obfuscator v1 seems to be the key that we were requiring. Even if we were unsure about that, it wouldn't have been difficult to brute force all the strings that we had uh, into the executable to jailbreak. Uh, this is the problem with non-obfuscated files. In order to solve this problem, we'll also try this on the obfuscated binary that we just created. We'll try to run the same strings command in the obfuscated binary. As we can see, there are no strings visible, uh, which means the string that we had passed it initially was obfuscated. It is not visible directly. So does that mean that it changes the output? Since we already know what the key is, let us try to run that and see if it works here as well. We didn't find the key, the string we were expected to find in the binary, which means it is correctly obfuscated. And a reverse engineer wouldn't have been able to jailbreak this thing that easily. But the output yet remains the same, which means it is also working fine as expected. In order to make this pass more robust, we have implemented certain test cases. These test cases include various edge cases in C and C++ programs. Uh, this is We are running a simple script that we have implemented to test if the test cases are running successfully or not. As we can see, all of the test cases are passing, which means there isn't any error in our obfuscation program. these test cases definitely help a lot in making these passes more robust. We just checked the working of the string obfuscation pass. Now let us verify how the control flow flattening and fake code insertion passes are working. To do that, we are generating visualizations. These visualizations contain the control flow diagrams, which are generated using another famous LLVM pass, that is opt dash dot, which is famously used to create graphics uh, illustrations of uh, diagrams, uh, which can be later converted into PNGs to visualize if they're visualize how they are working. We are doing exactly like that. The script just created this visual comparison report. Here we can observe all of the test cases that we just ran. We can select any one of them and verify that the control flow has actually been flattened. This is the current control flow of the obfuscated binary, and alongside it is the original binary's control flow. As we can see, there are several fake code blocks also being inserted in the program. Here, it will also show you how the reports are. Uh, Here we can see the change in executable files size, the change in intermediate representation file size, the number of flattened function, the number of flattened blocks, the number of strings encrypted, etc. This is another control flow graph which shows that the program has been flattened as expected, and there are fake code blocks inserted as well. Uh, this test case just ran only a single cycle, but we can also run multiple cycles. We will have a look at that later. This is the uh, obfuscation ran on a CPP program. The C++ program also shows that the control flow has been obfuscated, and uh, fake code blocks have also been inserted. This the makes the process of reverse engineering very difficult by confusing the reverse engineer. Now let us have a look at the web service that we have created using these obfuscation passes. This is Chakravyuha web service, where you can enter your C or C++ code, and that would be uploaded to the cloud, and the backend would run these passes on the provided code, and it would return the obfuscated binary along with a detailed report of how the how your program has been obfuscated. The users can select the level of obfuscation that they want, the number of passes that they want to obfuscation cycles that they want to run, or they can even choose to select which one of the obfuscation passes that they want to run. They can selectively run any one of string obfuscation, control for flow obfuscation, or even uh, fake code insertion pass, or they can run all of these three together. Since we had checked the generate CFG option, we can see the comparison between these CFGs of original and obfuscated files. As we can see, uh, the obfuscated binary has clearly flattened control flow along with few fake code blocks generated at them. The user can download the binary from here. They can also take a printout of the report that has been generated right now. The report clearly mentions all the parameters, such as number of passes run, the obfuscation level, the cycles completed, the change in intermediate representation sizes, the executable size metrics, and obfuscation results. The string encryption method that was used here was also mentioned here. The special features about the string encryption method are that the string encryption works very stochastically. It chooses one of the encryption algorithms at random. It can be any one of uh, algorithms such as SBox or a simple XOR swiper, or we are implementing AES256 as well. So that makes the pass very, very secure. Uh, these algorithms uh, are stochastic, as I said. So the for each of the strings, uh, a different encryption algorithm may be run, making the encryption string encryption very, very robust. We'll now use IDA, which is a famous tool used by reverse engineers uh, to reverse engineer software's executables. We'll simply just compare the analysis of IDA on the non-obfuscated and obfuscated binaries. So we first opened the non-obfuscated binary. This was the original binary that we had used obfuscation on in the terminal the first time. We'll open both of these binaries side by side and have a look at their codes and their comparisons. This is the obfuscated binaries code. As you can see, this is many different functions compared to the original binary. Here, the uh, control flow graph of the main function is a lot more complicated than it is for the original binary. This has many different blocks. A few of them are definitely fake code blocks that have been added via opaque predicates. So it is very difficult to analyze if they are live blocks or not. Comparing this to the original, there are very less blocks. Looking at the validate licenses function, we can clearly see that the string here is directly visible. It is not obfuscated at all. And if we compare that to the obfuscated file, the string isn't visible. Uh, a reverse engineer would have to find the decryption key, and he would then have to implement the decryption cycle on that for each different string differently. So that would mean it makes it very difficult to analyze. This is the report that has been generated for the obfuscation. It clearly mentions all the important parameters. That was all for the prototype from the team Chakravyuh. Thank you so much for listening.